All right, welcome back. I apparently didn't scare too many people off. Is there anybody here who was not here last class who was hoping to get in? Anyone? Anyone? Not yet. All right, well, before we get started, I have a few announcements. The first announcement is there will be a homework posted. It's already on the web page. I just have to put it on Blackboard because Blackboard will contain the correct submission instructions. Once I have put that on Blackboard, you will get an email at your NetID email address saying it's up. So you all, like, you're young and use, like, your twitting and stuff like that, right? But you heard of email? Old folks use it. I use it. So check your NetID email because that's where you'll get announcements for the class, okay? And they'll also show up on Blackboard, but I think Blackboard actually sends the announcement to you by email. The other thing, I normally have office hours today, but today I will not be in my office hours. My office hours are normally after class from 1 to at least 2, probably later. I just had to schedule a doctor's appointment today for that time. And I think there might have been one other thing I wanted to say, but it probably wasn't important. So, you all ready to get started? I'm glad you're here today. I'm very glad you're here today because today is the biggest Computer Science 1 day ever in the whole semester. It says so right there. Now, hi everybody. Hi. Much better. Get that out of the way. Today, like I was saying, today is the biggest Computer Science 1 day ever. In fact, today is the most important day of class. If you are not here, you're probably in trouble, okay? But you're all here, so that doesn't matter. Why is it the most important day of class? Because today, you are going to learn the one thing you really need to know about programming. The secret to programming success. In fact, if you only learn one thing from this class, this is the one thing that I want you to learn. If 10 years from now I run into you on the metro, which happens sometimes, and I see you and I go, hey, you're in my 071 class, and you say, yeah, I haven't touched a computer since then. I joined the Amish. I probably shouldn't even be on the metro, right? But I will say, I will say to you, what one thing do you remember from my class? And this is going to be the thing that I want you to be able to tell me. Okay? All right. Here it is. Oh, I just remembered the other thing I needed to ask you before we started, so just bear with me a second. Sorry about that. After class, I actually have to run over to the car barn. But I'm not quite sure how to get there. Can anybody give me instructions to the car barn? Car barn?
Yes. You know where Walsh is?
No.
Okay, so what you're going to do is you're going to...
Wait, Walsh?
Yeah.
No, I don't know.
Okay. So just, when you know where Louse steps are, right? Like.
What's the Louse step?
Okay. So you're going to walk out of the ICC from the third floor.
Mm-hmm.
Okay, like walk out of the front doors. Okay.
Yeah.
So then you're going to, hang on.
Okay.
You're going to want to, like, take, you're going to want to, like, swing right.
Okay.
And then you're going to want to walk past Copley, which is a dorm, and then you want to walk past Healy.
Mm-hmm.
And then you're going to want to follow the path that brings you towards Lau. And then you want to so that kind of brings you left. So once you hit the front of Lau, you want to take a left and take the stairs that go all the way down.
Yeah.
And then, so you go down the stairs. And then you walk down, N Street, so you're on 37th and N, so you walk to
N, like
the letter. And then you walk to 36th and N, and then you're going to take a right, and then you walk right until you hit Prospect and 36th, and Car Barn is right there, I think. I'm not positive, but yeah. Should be there.
Has anybody else been there? Do you all know where it is? Is that about right?
Between 36 and 32 on Prospect.
All right. So now I can get to Car Barn after class. Thank you very much. All right. Now you're asking, Clay, what are you doing? You just told me you were about to tell me the one most important thing that there was to all of computer science. All of it. And then you interrupted us to do that. Well, as you guess, I have an ulterior motive. What we just did is completely relevant to the one thing that is most important in programming. What did we just do in that exercise? We gave directions, and in this case, they were directions so that I could, after class, if I wanted, walk from here to the car barn, right? And what we really did was we created step-by-step instructions on how to get to the car barn. Now, why is this important? I know some people have programmed before. Why is this important? I don't know your name, but I know your program, so you have to tell me. What's your name?
I'm Eamon.
Eamon? Okay.
Because it's helpful in planning out a program for an algorithm.
An algorithm. That's the key word I was looking for. An algorithm. An algorithm is a step-by-step series of instructions on how to accomplish some task. That's what an algorithm is, a step-by-step series of instructions on how to accomplish a task. And here's the thing. Every single computer program is just an expression of an algorithm. A program, a computer program, is a step-by-step series of instructions that you give to the computer so that it can solve the problem for you. If you do not have an algorithm and you start writing a program, you are in trouble. Okay? It's important. Now, I said here, every computer program is just an expression of an algorithm. Where the word just hides the complexity of developing that algorithm. Now, when you do program, when you create a program, you are really creating an algorithm to solve a problem. Do you remember on the first day I said that I kind of know computer languages, but I really don't? What I understand is the underlying basis for how programs work. What I understand now is how to develop algorithms. Okay? And once you understand this, and it takes a while, you probably won't get it right away in one semester, you probably might get it in 2 semesters. Most people it clicks on the 3rd semester. That something in your brain just figures out, hey, I need to write an algorithm, I now have an understanding of how the computer works, and you just do it. But at first it's difficult, all right, because it's a new way of thinking. So this complexity is really the hard part of writing the program. Dealing with the programming language, dealing with the tools is also difficult, but once you master that, it gets easier. Right? This is the stuff we're really trying to teach you. You cannot write a successful program without understanding the algorithm you want to express. There will be a temptation for you at points in the semester to sit down and open up your code editor and start banging on the keys and banging out code. Okay? Resist that temptation. Don't get to that point until you have thought about your algorithm and you understand what it's trying to do. Does that make sense? It is the equivalent of if you had to write a paper about, somebody give me a topic, safe for class topic. Abraham Lincoln Vampire Hunter, which I actually watched over the weekend. I enjoyed it greatly. If you had to write a paper about Abraham Lincoln, right? If you just sat down and started banging out Abraham Lincoln facts, right? He was a president, he had a beard, he cut down a cherry tree, maybe that was someone else, some sort of trees, right? Your paper would come out sounding like a 4th or 5th grade paper that was just a bunch of unrelated facts because you hadn't taken the time to try and put everything together. The same thing will happen with your program. If you just sit down and start programming without thinking about the algorithm, you will get in trouble. Because what will happen is you'll develop a program that does something, but not the right thing, and then you'll have to figure out not only what your algorithm should have been, but what your program is currently doing and how to get it there. Okay? So, let's reinforce this because it's important. Have you noticed I'm spending some time and emphasis on this? An algorithm is an ordered series of steps used to perform some task. A program is an algorithm expressed in a form that a computer can execute and a human can understand. Both of those two things. Let's look at them separately. In a form a computer can execute. You must specify an algorithm in terms of what the person who is following it is capable of doing. Does that make sense? So, for example, what was your name? Rebecca gave me the instructions on how to get to the car barn. She told me things that I was capable of doing, right? Were she giving directions for Superman, that would be different than those for Batman, right? If they were here and had to get directions. If Superman were here and he said, I must get to the car barn, what would you say? Just rocket straight up, right? Get about 500 feet up and look for a river. And when you see the river, you'll see a bridge. There's a bridge right there. Just go towards the bridge, and there's a building with a flat top and a white gazebo there, and that's the car barn. And Superman would go, yeah, and he'd bust through the roof and he'd be gone. I sadly cannot do that, right? If Batman were here too, he would say, I'm the Batman. Give me directions to car barn. This is why I'm a professor instead of a comic, right? And you would give him essentially the directions you gave me earlier, and then you'd say, don't worry, Superman already took care of it, right? He's already there. So the directions that you give have to be something that people, the person or the machine or whatever is executing it, can follow. Now, computers are really very limited in what they can do. They're exceptionally limited in what they can do. And we're going to come back to this and talk about this in detail shortly. So remember the other part? A program, an algorithm expressed in a form that a computer can execute and humans can understand. The reason for this is that programming is a team sport, except in this class and many others that you'll be taking here, because you're working on developing things, your individual skills that you can bring to the team later. Now, if you're writing code and the code is not easily understandable by people, that is a problem. So when you write something, there are many ways to create an algorithm for a problem that a computer can solve. There are different programming styles. And as you program more, if you choose to remain doing this, which I hope you will do because it's fun, you will develop your own programming style. And you'll have a chance throughout the semester. We're going to share code. Once we've written the projects, we're going to put up almost all the code in the class, and you will be able to look and see how your classmates solved problems. And you'll be able to look and see how other people's styles developed. And you'll be able to develop your own programming style. All right? A lot of people who program, who've learned to program themselves, haven't kept this part in mind. Right? If you teach yourself to program, it's good enough if you understand your code. It's not as good. Most people don't practice writing codes for other people to read. Now, if you haven't programmed before, I'm inviting you to listen, but you don't really have to pay attention for the next few slides. If you have programmed before, let me just address you directly. Some people, when they're programming, try and keep in mind what is going to be the most efficient solution for the computer. And they will write the most efficient solution, even if it makes it harder for humans to understand. I'm just going to tell you, performance doesn't count for this class. If you write a program that expresses an algorithm that solves the problem, that's good enough. It doesn't have to be fast. That doesn't mean, it should take forever, but in general, it has to actually finish. How's that? Performance doesn't count for this class. Making your code run faster, if it's something you're worried about, can be done after you have developed your program and your algorithm. You develop your program, you develop your algorithm, you run it, and you see how fast it is. If it is too slow, then you spend time making it faster. Now, I'm going to tell you, most of the time, this doesn't even need to be done at all. If you choose a good algorithm, most of the time, the way you write your program makes such a small difference that it's hard to see. If you're doing something that's critical, you can get tools called profilers that will help you analyze how your code is running, and you can make the parts that need to run faster, faster. But for most of us who have never programmed before, we don't need to worry about programming. If you have programmed before and you're worried about performance, don't. Okay? Make your code easy to read. I end up reading a bunch of code just in part for my research and in part because occasionally I'm asked to testify about patent cases, about code, if it infringes on a patent. And some code is just wonderful to read because it's very clear and easy to understand, and some of it is horrible. I really strongly encourage you to write your code cleanly. All right, so let's re-summarize our summary because it is important. A program is an expression of an algorithm. What's a program? Let's try again. What's a program? Exactly. To write a program, you must know what algorithm you are trying to express. Okay? So let me just say, here's what's going to happen over the course of the semester. I think I was going to talk about this later, but I might as well talk about it now. You're going to write 5 kind of big programs. For the first 2 or 3, I can't remember which, I think first 2, I'm going to ask you before you write your program to turn in a design document. I'm going to ask you to write your algorithm in a form that is not a C++ program and give it to me ahead of time. And the reason for that is to force you to think about your algorithm ahead of time. Now what's going to happen is I think around project 3, I'm no longer going to require you to turn in your design document. And do you know what's going to happen? Most of you won't bother to do it because I'm not requiring you to turn in, and there'll come to time to program and you will fall into a pit of miasma and despair because you haven't done a good job specifying your algorithm. You just started typing stuff. Okay? And we'll talk about after project 3 is turned in who did that, and then I'll tell the people who did that I told you so, and I will feel better about myself. So. All right, so I like to give you all little breaks. Time for a little break. Stand up and stretch if you like. We'll just stand here for a minute. All right, does that help? All right. Remember earlier I told you that computers are very limited in what they can do, right? They are very, very limited in what they can do. Now, you all don't really believe me, but let's talk about what computers can do. And when we're talking about what computers can do, I really mean the hardware part of the computer, the physical hardware in the computer. Later, probably next class, I will give you a deeper understanding of how computers work, okay? How they do it. But right now, we're just going to talk about what they can do. So, here's what computers can do. Math. That's it. Doesn't sound like much, does it? Let me make it worse. What they really can do is arithmetic. Computers can add, they can subtract. They can compare two numbers, mostly by subtracting and seeing if the result is positive or negative or 0. And, oh, they can store a lot of stuff, right? They can store lots and lots of numbers. And they can add them together, they compare them. That's all they can do. A computer is a tool that does nothing but manipulate numbers. And when we talk about them and how they work, you're going to see that these numbers are really just binary numbers, ones and zeros. So a computer, all it can do is manipulate ones and zeros, right? You look skeptical. Computers are actually completely stupid. They are. Computers are dumb. Everybody repeat after me. Computers are dumb. They are. They're very dumb. Whoops, wrong way. So, if computers are so dumb, how can they do all this cool stuff that we know and love? Like delay my voice for 3 seconds at the beginning of class, or project PowerPoint slides, right? How do they do this if all they're doing is manipulating numbers? Computers are stupid, but they are stupid very, very fast. Very, very fast. And in fact, they are stupid unimaginably fast. You can take a little bit of stupid and you can't do much with it. But if you have a lot of stupid, you can do quite a lot with it. Okay? So let me talk about this. Let's have an adding competition. Here's what we're going to do. Everybody get ready, and you are going to add up some numbers. The numbers will flash on the screen. You're going to add up the numbers. I want the first person, as soon as you finish adding up those numbers and you're ready to tell them to me, raise your hand. In fact, I'm going to time it. We're going to see how long it takes. It's okay. The first person in the class is going to be the first person, and I'm not going to wait for everybody to finish. The fastest person in the class is going to set the time on behalf of all humans. Okay? So no pressure. All right. So I have my stopwatch. All right, let's set a few rules. First of all, you can use any mechanical stuff you want, pen, a pencil, abacus. If you got log tables, you can use those. Slide rule. Anybody even heard of these things? Pen and pencil you probably heard of. Abacus. Okay. What you cannot use is anything electronic. Sound fair? Now let me give you a piece of advice. I'm going to flash the numbers on the screen. If you take time copying them all down, that's going to be really slow. Okay? So I encourage you just to use your head and write down the answer as fast as you can. I did this at home the other day. I'll tell you my time afterwards. All right, everybody ready? On our mark, get set, go. Oh, ready? Oh, sorry. All right, now are you ready? On our mark, get set, go. Come on, add them up. Yes. Yes, sir. Congratulations. All right. Your time was 22.2 seconds. My time was 26.6, so you are much better at math than me. So it took 22.2. So let's actually look at something. I actually set up a little spreadsheet to work this stuff out. I think I did it when the screen was bigger, so let's try that. All right, so we took 22.2 seconds, which means that you're only 59.94 billion times slower than a computer. All right? A computer, a standard computer, like my laptop right there, can add on the order of 2.7 billion numbers a second. 2.7 billion numbers a second. The time to add any two numbers is measured in fractions of a nanosecond. Now, this is a lie, a little bit. This is just an estimate. In fact, computers can sometimes do this faster, sometimes they can do it slower, and computers have the advantage of while you can only add up one number at a time, they can add up tens, hundreds, or thousands of numbers at the same time. Okay? So this is really fast. The computer is essentially 59.9 billion times faster than the fastest adder in our class. You were very close to over there. Okay, so let's put this into terms we might be able to understand. A computer can add up as many numbers in a second as you can in 1,899 years, assuming that you do not eat or sleep. If you include eating or sleeping, it's going to take you almost 5,700 years to add up all the numbers a computer can do in 1 second. This is about 72.4 lifetimes, assuming you live the human average of 72 years, and you start adding the second you're born until you die, except when you're eating and sleeping. Okay. Is that crazy? It's insane. It's absolutely insane how fast computers are, okay? It's nuts. You don't seem impressed. I think it's utterly incredible. The computer can't do much, but it is so amazingly faster than we are that we can do just cool stuff with it, okay? It's almost impossible to imagine, right? How many of you can imagine spending 72 lifetimes doing nothing but adding up numbers? No one. No one can imagine that. So let's try some other stuff. The fastest human can run 100 meters in 9.58 seconds. This is not me, right? Just let you know that. Nowhere near that. If a computer was proportionally as fast as it was at adding up numbers, the computer could run about 8.1 million kilometers in that time, which in fact is about 2,820 times the speed of light, so that's actually not going to work, because we can't really imagine going the speed of light, can we? All right. That's a bad analogy. What else can we try that you might actually understand? Well, how about this? If computers produced urine proportional to people, right, the average daily urine production for people, a computer would produce about 4 Potomac rivers worth of flow per day. That's pretty incredible, isn't it? And it would be problematic for the plumbing they have in your office if they did that, so we can be glad they don't. All right, anyway, computers are so fast, they're just unimaginably fast. And that's just one computer, right? Just one computer. It's incredible how fast they are. Are you all impressed yet? Have you ever thought of computers this way? I mean, a computer is a tool. It's dumb. It's really dumb as a box of rocks, but it is so fast at being dumb that you can do amazing stuff with it, right? You can just do a lot of, if you just have lots of numbers that you can store and you can process them and add them very, very fast, you can do an incredible amount, absolutely incredible amount. And I'll just tell you, today, the way computers are moving is not just having one processor in a computer, it's having multiple processors. And if anybody has looked at like what your graphics cards, anybody have a desktop computer? A few of you, they're going away. But now they have these amazing graphic cards. And in the graphics cards, they have separate processors. And there's thousands of them in there. You can buy a single card that has 4,000 processors. And you can put it in there, and then you hook it up with your other one, and you put like 2 or 4 of these in there, and you get like 16,000 processors. And these processors can all do that much math in parallel. And that's how, video games and movie rendering all happens. They built a mathematical model of a scene, and then they individually trace the path each ray of light takes. And when it hits something, it figures out what the surface is like and how much it's going to diffract and reflect. And it's all just a big mathematical simulation. And the reason it can be so detailed is because we just have this sheer amount of computational capacity. We can just crunch lots and lots of numbers. We have huge amounts of stuff. All right. So given that the computer's stupid, let's look at what we can actually do when we design algorithms for these things. Okay. Who's with me, by the way? Good. Who's against me? Just checking. All right. So one of the things we can do, obviously, is we can start running an algorithm. We can say, okay, computer, start doing this. And it goes off and starts doing it. Just like we start, except on a computer, an algorithm is not called an algorithm. What's it called? And what is a program? An expression of an algorithm. What happens if you start programming without knowing what your algorithm's going to be? You're going to have a bad day, okay? I meant to find the actual South Park picture and put that up, but I forgot to do that yesterday when I was making these slides. I'll add it next time. All right. Once the program's running, we can actually tell it to stop, which is good, because we would like our stuff to stop when it's done, right? Otherwise, it will never be done. We can read input. This is also very useful because when we develop an algorithm, we want to be able to use it in different situations. And even though the same algorithm is running, the way we set up these different situations is to give it different input. We can have it show output. How many of y'all think this is good too? All right. It's good because then we can see what the results of the computation were. And finally, we can perform operations. And the operations we can perform we'll go into, but I'll show you next time when we talk about computers, the operations aren't very much. Math operations, comparison operations, that's really about it. Oh, see, I said comparisons too. I forgot. Okay, comparison operations. And that is about it. But we can do lots and lots and lots of these, and they can do them very, very, very fast. Okay. All right, so one of the things that happens is even though computers provide this kind of low level of functionality, it's really annoying, it would be really annoying if every time you had to write a program, you had to start from scratch, right? And you had to start from the very lowest level and build it up. Well, programmers are lazy, and I encourage you all to be lazy, but be lazy in the good way. Lazy in a good way means minimizing the amount of work you have to do to accomplish what you're going to do. Okay? I'm very lazy in that sense. It drives my wife crazy. I will argue about how to do things if I see an easier way, and I will actually spend more time arguing with her about it than it would have taken just to do it her way. But this isn't my therapy. I'm sorry, I should stop that. All right. So what ends up happening is programmers develop things called libraries, where you can just take advantage of the algorithms that they have created in your own algorithm. You can think of these as kind of sub-algorithms, right? So instead of having to build every single program out of tiny pieces that the computer supports, you can build your program out of these larger pieces that other programmers have already created for you. Right? Does that make sense? And what's going to happen is we think about these sub-algorithms, we can call them libraries. Later in the semester, we're going to teach you how to build your own sub-algorithms. Okay? So that you can build your own little pieces that you can reuse over and over and over again without having to start from scratch every time. Now, I'll just put an aside here. The language you're using is C++. C++ is a relatively low-level language. There's actually a bunch of stuff. But other languages you might have heard of, like Java. Anybody heard of Java? Python, Ruby, stuff like that. Those languages provide actually much more infrastructure and useful things for you than C++ does. The reason we teach you in C++ is because C++ has a very rich set of features related to other programming languages, and we can teach you more about programming in C++, even though sometimes it requires more work on your part. And C++ is very fast if you're worried about performance, which we're not. All right. So given that algorithms are important, we cannot create a program without an algorithm. How do we express algorithms in a way that we can think about them, right? Because Didn't I tell you you're going to have to think about your algorithms before you program them? Yes? No? All right. Okay, good. Just checking. Okay. So how do we represent this? Well, the first thing we're going to talk about is a flow chart. The flow chart is the primeval representation of a computer algorithm. Back in the day, before I even started doing computers, which you can tell was a long time ago, my grandfather worked at IBM. And back in those days, computers filled up a room, maybe not as big as this one, and they cost millions of dollars, and they had less computing power than the watches some of you are wearing in the classroom. All right? But they were a big step ahead what people could do. They were very expensive to program on. It was very, very expensive. And programs were put on punch cards. You ever heard of punch cards? Every instruction would be a separate card that had holes punched in it, and you would feed this in the computer and it would see which holes were there, and then it would execute that instruction. So every single step of the algorithm was a separate card. And you had these big racks of cards that you would carry down, and you would put them in a cubby, and when it was your turn for the computer to run your program, they would take the cards and they would slide it into the computer and it would go and it would go through all the cards and run your program, and it would print some output, and they would put it back in your cubby, and you'd come back the next day and get it. Okay? It took a long time. So it was an emphasis on making sure your algorithm was right ahead of time. So what they developed was this technique called flowcharting, and you would essentially draw a giant picture of your program before you programmed it. And once you had this giant picture, you would write your program and you would verify that each one of the cards matched the step on the flowchart, and then you would send it off to execute, and it would run, and it would be done, and you would hope it was right, because otherwise, if it wasn't, if you forgot like one small little thing, you had to repunch that card, submit it, and then wait another day. So nowadays, you know, computers are cheap. We can do whatever we want. So flowcharting was really very popular back then, and it's a good way to understand how algorithms work. So we're going to take a look at it. So a flowchart consists of a different set of symbols, and we'll see more of these as we go along. The first one of which, and one of the most important, is the start symbol, because this tells you where you are going to start. So if you're doing a flowchart, you figure out where the start is, and you start there. Now what happens is each one of these symbols is going to have a line with an arrow on it, and we're going to connect a whole bunch of these together. And you're going to start with the start symbol and follow the line from place to place. And this line represents the flow, the step-by-step flow of your algorithm all the way through. Now, we also want to do input, right? Didn't we say input was useful before? The input box is a parallelogram. It can represent input from the keyboard. It could represent a mouse. It could represent different things. What I'm showing you here is actually a simplified set of flow charting instructions. Back in the day, they had these big plastic templates, like stencils, and they had different symbols for input from different places, but we don't really need that. Operations, if you're going to do some sort of calculation, occur in a rectangular box. And one of the things we can do is we can make decisions. A program that just went in a straight line from top to bottom would be boring. Doesn't mean it's not useful. It just means it's boring. Particularly if we wanted to write a game or something, right? If you're playing, I don't know. What's a cool game these days? Candy Crush. Yeah, say Candy Crush. Every time you played Candy Crush, everything happened in exactly the same order, right? And you only got like 50 candies and then it stopped. That would not make them any money at all. What was your game? Oregon Trail? Y'all still play that? Oh, yeah, that's right. All the cool stuff is coming back on phones. Okay, so decisions allow us to take different paths. And as we're going to see later, decisions also allow us to go back, right? This program just goes from top to bottom, but we can also use decisions to go back. Sometimes we're going to want to do output. Output uses essentially the same symbol as input for us. And then we're going to stop. And the stop symbol is similar to the start symbol. Now here, I've drawn the arrows flowing to the both to the same stop symbol. You don't necessarily have to do that. You only have one start, but you can have many stops if necessary. So this is a flowchart that represents an algorithm that has a series of steps. So let's just take a look and see what this algorithm does. Where do we start? Where it says start. And what do we do from there? follow the line, and we reach this box that tells us to do. So let's say we input a number, okay? Just an integer, a number with no decimal. Somebody give me a number. Excellent, 1. So we input 1, and we go to this operation. This operation, which I didn't say in here, let's just say that it divides the number by 2 and tells us the remainder. Okay? So 1 divided by 2 is? Yes, but if we're doing integer division that doesn't have a remainder, 1 divided by 2, 0 with a remainder of 1, right? So, and then we go to a decision. This decision can be, was the remainder 1 or 0? In this case, it was 1. So we can say yes, and yes goes to output. And here we can output that that number was odd, right? If you divide something by 2 and there's a remainder of 1, that number was odd. If you divide it by 2 and the remainder is 0, something is even. So this is an expression in flowchart form of an algorithm that if we put the right computational steps in each box, would tell us whether a number was even or odd. Okay. Pretty simple algorithm, right? Yes. But because the computer is stupid, we have to break it down into these clear steps. If I asked you, is 1 even or odd, what would you say? Some of you would say odd, some of you wouldn't speak at all. That's fine. But how do you think about that? Well, you're like, doesn't divide by 2, it must be odd. But the computer doesn't understand doesn't divide by 2. What it understands is math. Get a number, divide it by 2, keep the remainder, check the remainder. If so, go one way, if not, go the other. Does that make sense? So the steps that you have for your algorithm have to be very explicit when you program. All right, so the question is now, what if you do something very often in your algorithm? Let's say that we give you a list of all the ages of everybody in the United States. How many people is that? 360 million roughly, right? How many of you all want to go through a list of 360 million people and determine how many people have odd ages and how many people have even ages? Anybody? You might be able to accomplish that in your lifetime. You might, but you might not. The computer can do it though, and how long will it take? Probably like a minute, right? Not very long. So if you want to do something in your algorithm over and over and over, like determine if a number is even or odd, what we can do is make a sub-algorithm out of it. And these sub-algorithms will go by different names depending on the language, and I will give you more formal terms for these later. All right? But I want you to have this idea that you can build small algorithms and then link them together to build something more powerful. So here's how you show this in a flow chart. You build this box that has these extra lines in there, and you give it a name. In this case, we might give it a name even or odd. And what this means is really when you reach this box, go and perform this whole series of steps. So the box with the lines on the side now represents this entire set of operations that we might have done otherwise. Right? And we can take this piece and reuse it. And in fact, if we wanted to rewrite our first algorithm and just use that, it would look like this. Start, figure out if something's even or odd, stop. And we could use that over and over again elsewhere. So we can build up things out of small pieces. All right. How's everyone doing? I'm going to stop for a minute. This is the first time I've actually taught this class off of slides. I almost always draw things on the board. I kind of like doing it better that way. This semester, though, we have what's called an ITEL grant, which is to improve the technology teaching in the classroom and try and create video and recordings and stuff. And I found that it's going to be easier to use Keynote. So the problem with that is that I probably go faster than I would if I were drawing things on the board. Oh, by the way, how many of you are bored out of your minds? This is really simple. Come on, you don't have to lie. Yeah. Now, what did I warn you on the first day?
That if we don't pay attention to this.
Yeah. It's boring and then later it gets harder. Okay, so I'm living up to my word so far, right? All right, so we have this grant to record, so I'm doing it on Keynote. I probably go faster on Keynote, and I probably don't stop as often for questions. All right, but I do want you to feel free to ask questions. Don't be shy, really. Who has a question? Of course. Yep. Oh, and by the way, I'm going to post all these videos online through Blackboard, so you can go back and look at them if you want. And that's the other thing, where I have these pictures, I'll probably end up going a little bit too fast for you to copy them all. So if I'm going too fast, somebody just say, hey, time out, let me copy it. I'm not shy about things like that. Okay, I'm not going to be offended. Who else has questions? 17-second rule doesn't apply in this class. Just ask them right away. Who would have questions if there was a piece of candy? Oh, yeah.
So you can put sub-algorithms on top of sub-algorithms.
Yes.
To create like a long.
Absolutely. And in fact, when you're programming in C++, you're going to be doing quite a lot of that. It won't be apparent right away. I'll kind of mention it. But yeah, it's algorithms all the way down.
So like when we're like writing language and code and stuff, do you have to cite the sub-
No. No, the sub-algorithms are going to be provided as part of C++. Like the language itself is constructed of a variety of things that'll help you. But thank you for asking that question. Yeah, you can just use any C++ feature without having to cite it. It's just if you go out someplace and you find code that solves an algorithm and you incorporate that, then it would be appropriate to cite that. So. All right, so oh man. All right. Any other questions? Do you want to stand up for a sec, stretch out? No? You happy? Come on, stretch out just for a sec. I kind of judge by when people need a little break by how far lean back around us. All right. So we've just spent some time here discussing flowcharts. So let me ask you answer this question. How are we going to use flowcharts in this class? Because they are kind of bulky and they are unwieldy. And the answer is we aren't going to use flowcharts in this class. Except for one circumstance. And that's the circumstance that I will occasionally show you a diagram of how something is working in C++ by drawing a flowchart about it. Okay? The reason I introduced them is because they're a really good way of like thinking about, in terms of your algorithm, you really do have to have this like linear, do one thing, go to the next, go to the next, go to the next. All right? The hard part about programming at first is understanding how to construct your algorithm in very small steps in this sequence. Okay? That's the thing that is actually, constructing the algorithm is one thing, but understanding how to construct the algorithm out of those small steps is another. So we're not going to use flowcharts. They are very useful to envision the flow of the algorithm, though. It's just that they get kind of bulky and unwieldy because we actually have more computer time than they had in the 1950s. And since, again, the algorithm is a series of ordered steps, the flowchart makes that order very explicit. And the hard thing for people who are learning to program is the explicitness of the order. People will know they have to do something, like people as in students and beginning programmers will know that there's something they have to do, but they have a hard time figuring out kind of where it goes, like where the order is. All right? So I'm trying to make clear that we have this very explicit step-by-step order. So how else can we represent algorithms? Actually, somebody give me another example of an algorithm. Anybody have any other algorithms they're aware of? Yes, sir. Yeah, that's a particular type of computer algorithm, but in daily life, we encounter algorithms all the time. Yeah? Driving directions are absolutely an algorithm of how to drive somewhere. What else? Yeah? Cooking. Cooking is the classic one, right? Your cookbook, if you ever have a cookbook or you look at recipes or online, is really an algorithm to program you to produce food that you can eat. Right? So in terms of things that we know, algorithms, we already deal with kind of dealing with algorithms, at least in those cases. And there's probably others, right? Anybody ever bought IKEA furniture? You will pretty much the moment you graduate from college, I guaranteed. Right? You move into your own place, everybody just buys IKEA furniture. And it comes in these like incredibly dense packs and you have to read the instructions. Anybody ever put together a bicycle? Yeah. All these things are algorithm. Like anything that has this step-by-step series of instructions is algorithm. So how else can we represent algorithms? Well, some algorithms for people we can represent by like driving directions, by like recipes, by building instructions, things like that. But one of the things that we're going to do in order to think about this is we're going to use an outline format. Now the outline format is actually pretty simple because we only really have these operations. Same ones we talked about before. Input, output, calculate, decide, start, and stop. That's about it. Now what's going to happen over the course of the semester is you're going to see these calculations. We'll have a lot of different types of calculations we can do, building on kind of the libraries and sub-algorithms other people have created, and input and output and stuff too. So here is an outline format of essentially what I described for the flowchart. Where do we start? At the start. In outline form, what's going to happen is everything is going to go step by step from top to bottom. Okay? Step by step from top to bottom. So the first step is input. Please tell me a number. Oh, sorry, the first step is really start. But after the start, the first step is input. The first step is tell me a number. Where do we go from there? We go down to the next step, right? The order here is implicit from top to bottom. We go to calc, and we divide the number by 2. From there we go decide, is the remainder 0? Well, I got that backwards, didn't I? Excuse me one sec. All right. Like I was saying, we divide by 2 and we decide, is the remainder 1? Now here it's a little bit different because in the flowchart we had branches and we could explicitly follow branches. Here what we're going to do is we can use some language like if so and tell what we're going to do, and if not, tell what we're going to do. And in this there's an implicit assumption that if you do the if so, you skip all the stuff in the if not, right? So there's a flow from top to bottom, however, in decisions you can skip parts of the code. And we use indenting to show this. Right? We have indented the if so, and we have indented the output to show that it falls under the if so, or the if not. And then we stop. Sir?
Is there why the output odd is indented more than?
Yes. Then this one? No. PowerPoint error. Sorry. I thought I fixed that yesterday. But no, the idea is that this is indented to show that it lives with the decide, and this is indented to show that it lives with the if not. If you had multiple statements, they would all be indented the same. Kind of pushed in like that. Okay. And you're going to see when we get to programming C++ that in fact C++ looks a little bit like this. Just a little bit. So this is how we're going to do things. Now, we're going to use this on the first homework. The homework is going to be, I'm going to finish posting that tonight. It's up right now. You can start looking at it. Though you have to go to the class webpage, which is on the syllabus, or you can just search Clay Shields on the first hit, go to my webpage, hit teaching, and then you'll see the class there. But it's on the webpage. I'll send out a link to it when I post the homework through Blackboard. The instructions say turn in something written. It's actually going to be submitted through Blackboard electronically, because that's easier. Okay. So that'll be posted today, and you'll use this on the first homework. And you're going to use this on the project design documents. This is what I was talking about for the first 2 projects. You were going to turn in designs before you actually write the programs to force you to think about your algorithm. All right, so what are we going to use for the programs? Pascal, C++. All right, C++ is a language that allows us to represent an algorithm in a way that the computer can understand. Sort of. Here's what happens. You're going to write your code in C++. C++, the computers can understand and people can read. And it's a notation for algorithms that can be executed on a computer in line with the computer's capabilities. The thing is that the computer really only understands C++ and can only execute it with help from a compiler. Now, if you haven't heard of a compiler before, I'm not surprised, because you haven't programmed before. A compiler is a tool that turns this readable C++ code into an executable that the computer can understand and run. The computer does not understand C++ directly. It understands a binary language. If I had time to do a Star Wars reference, I would reference Star Wars 4, where C-3PO says that he speaks the binary language of like moisture evaporators or something like that, right? Because they only understand binary stuff. So the compiler turns this C++ code into a computer executable. So let's look at the algorithm you will use to do this, okay? Because there is a process that you will use in creating and writing your program. And here it is. Where do we start? Except in this class, where do we start? Start early, okay? We don't just start, we start early. Why do we start early? Because you can get help. When you get stuck on something, if you have started early, you can get help. If you start late, there will not be time to get help, and you will just be stuck. All right, so here we are. We start early. We read the problem. I'm going to post these programming assignments on my webpage. You can go and look at them. You can read through them. You can understand them. A hint I will give is that they are similar from semester to semester. And in fact, past semesters, projects use many of the same language features. It may even help you to go back and look at the past assignments and their solutions to get an idea of what it's expected to look like. Okay? You don't have to cite that if you want. So you read the problem and you understand what you're expected to do. That is your input. Your next step is to spend time developing your algorithm. If you do not spend time developing your algorithm before you program, life will be difficult for you. It's more difficult that way. Next, let me just go back to this and tell you some stories. I'm at the point now where I don't always sit down and design an algorithm because I can think about it pretty hard and come up with like an idea of how everything's going to work. So once I spent like 2 weeks writing code, and I got down to the end and I had this problem. And I was like, gosh, this is a weird problem. I have this sub-algorithm which needs this sub-algorithm to work, but this sub-algorithm needs the other one to work. So I had this like circle where each one depended on the other, and you can't compile code that way. And because I did not sit down and think about my algorithm in advance, I spent like 2 weeks doing this, and then I got there and I was like, oh, and I had to rewrite like a whole bunch of stuff because I didn't do a good design up front. All right. If you ever end up as part of a large programming team, the coding part of what goes into programming is actually not the big part. The big part is everybody who's working on the project sitting down together and figuring out the design document and figuring out how things are going to be designed. And then once you figure out how everything's going to be designed, you actually go and write the code. In some forms of software development. There's also some forms of software development where you meet for 5 minutes in the morning and say, I'm going to go do this, and other people do that. And different things work. But for you all, designing the algorithm is best. I don't even know why I said all that stuff I just did. I hope you enjoyed it. Okay. All right, once you have your algorithm design, that's when you start writing code. And you use a tool called an editor. An editor is literally what it sounds like, a tool that allows you to edit things. And you write up the code that implements that algorithm. At this point, you will have a bunch of C++ code in a file. And now you reach the point where you use the compiler and you compile the code. Now, I warned you last class about the compiler. What did I say about the compiler? Anybody remember? It's very rude. The compiler is very picky and very rude. So what will probably happen when you compile, if your code is not syntactically perfect, if every single little C++ feature is not exactly obeyed, you will get a message that says you have some errors. Now, if you get this error message, here is my advice. Only look at the very first thing it says. Don't look at the whole list and tear your hair out. Just go, oh, I made a mistake. I'll fix the very first one. So look at the output. If there's errors, you go back and you edit your C++ code and you fix that error. And then what do? You compile again and see if you have errors. So you go through this little thing where you're going back. Okay? This is called a loop. And later in the semester, we'll talk about how we do this in C++, but this is a loop where you can go through the same sequence of instructions a number of times, or forever if something goes wrong. All right, except hopefully compiling your program and editing won't take forever. All right, so if there is an error, you go back and edit your code. If there is not an error, then congratulations, your code is syntactically correct. That means all the C++ stuff is correct, but that does not mean your program is doing the right thing. Your program can compile safely, it can compile cleanly, and you can run it, but just because you can do that doesn't mean it implemented the algorithm that you intended it to implement. Okay? It's kind of like you can write a paper, your paper can pass the grammar checker in Microsoft Word, and you won't have all those underlinings. That doesn't mean your paper makes any sense. Right? We can say things that are syntactically correct that don't make any sense. Probably like what I'm doing a lot today. All right, so when we're done, you actually run a bunch of tests. You get your program and you run and you test to make sure it's doing what you think it should and what you expect. Now you have to make a decision. Is your program correct? When you run your test, does your program give you the correct output? If the answer is no, well, now you have to go back and reconsider if you designed your algorithm correctly, or if you have some other type of error in your program, right? It could be that you created a C++ program that is syntactically correct, but you put a plus where there should be a minus, you put a greater than where there should be a less than. By the way, you're going to see me do that like 50 times over the course of the semester. When I'm typing code, I'm going to put the greater than and less than the wrong way. I always do. And then I check it and I go, oh yeah, that's right, and it's still wrong. Okay, that's like my superhero flaw or something like that. Okay, so you're going to design your algorithm. You have to reconsider whether if the test doesn't work, if it was an algorithm problem, or if there was a problem in your C++ code that has to be fixed. So you try to fix it, you compile it, you go through this again, and eventually you go back and you test again. And at some point, you will decide that your program is correct. And at that point is when you have some output. You will submit code. This semester code is going to be submitted using Blackboard. You'll upload it to Blackboard, and then you'll be all done until next week. All right, so this is the algorithm that you'll follow in preparing your assignments. And what's going to happen is this week's homework is about algorithms and thinking about algorithms. Next week's homework is about this process right here. We're going to give you some code to type in. You don't have to create the code. You don't have to create the algorithm. All you have to do is edit it, compile, get it to test and run correctly, and submit it. And that's to teach you to use the editor and compiler before you have to step up to creating your own programs with it. Okay. Does that make sense? Who's with me? Who's against me? That's how I know who the smart Alex in the class are. There's always somebody who raises their hands for that. So, all right. Everybody had a chance to copy this down? Or at least you're going to look it up online later? Because this is literally what you're going to have to do. There's going to be a little instructional video on how to do this steps and use some of the stuff that will be posted as well. Okay, so in this class, we've talked about a bunch of stuff. We've talked about algorithms. What is an algorithm? I'm going to, pardon? An algorithm is a step-by-step series of instructions about how to accomplish some task. Okay, step-by-step, ordered, and the instructions have to relate to the thing or person who is receiving them. They have to reflect what they can do. We've talked about some representation of algorithms. We talked about flowcharts and outlines. I stepped you through a flowchart of what you're going to do in class, which was this algorithm for programming. Oh, we also talked about like how incredibly fast and awesome computers are. They're just, there's nothing in the physical world that compares to computers. Absolutely nothing. And there's nothing left to get into but C++.